the general broad topic, and I'll try to incorporate some kind of quantum probability things as well. But roughly, the topic is a kind of categorical, category theoretic language for probability theory. And so I want to kind of compare this language with the traditional one, so the traditional language with the measured theoretic probability, right? Based on Kolmogor's axioms for probability measures and probability spaces. And with this contrast, this is I want to compare this with the categorical approach with Markov categories. And roughly, I want to compare this with saying that working in measured theoretic probability is analogous to programming a computer in machine code. That's the analogy that I want to make. And the good thing about machine code is it's very powerful, right? And you have kind of very fine-grained control over the computer. You can basically optimize your code as much as you want. But in practice, obviously, almost nobody is going to program their computer machine code anymore because it's just too complicated for a human programmer. So we need something more high level. We need a more abstract language. And that's why we have, well, higher level programming languages. And so the analogy that I'm making is that categorical probability and Markov categories in particular are the higher level language for probability. And my hope would be that at the end of the week, you'll all see and understand why I'm saying this and hopefully agree with me as well. But feel free to, yeah, I mean, that's up for debate, of course, as well. Okay. Any questions so far? All right, then let me give a kind of an overview over what I want to do today and the next few days. So today is more like a kind of introduction. I'll present the definition of Markov category and a bunch of examples and some of the kind of most basic concepts about Markov categories, like determinism, additional axioms, concept of almost sure equality, things like that. And then tomorrow, I want to get to the Definetti theorem. And well, so I know that some people here are interested also in quantum classical transitions and this kind of thing. And I think it's in a bit of a similar flavor. And maybe, so depending on how things go today and how, let's say, how much in depth I can go tomorrow, I may give a purely categorical proof, or I may at least say that there's one. So this is just a kind of one of the examples where you do not need to go to the machine code to state and prove that the Definetti theorem can be completely done on this side. Okay, and so then on Wednesday, I'm going to get to lots of large numbers. Obviously, one of the most kind of central concepts of probability, and also closely related to the Definetti theorem. And so this is kind of quite recent work, and we're kind of done with the paper about this now. So this is kind of our latest stuff. And finally, on Thursday, given the audience, I want to say a bit about the quantum probability and how one can potentially deal with quantum probability in this kind of approach. And this is so far much less developed than the classical case. And yeah, I'm going to present then two different approaches to this quantum and evaluative Markov categories. On the one hand, to categorical quantum probability, but also the idea of what we call semi-Cartesian probability, which is more like an abstract approach to these generalized probabilistic theories. Okay, so this is my outline. And yeah, since so far everyone seems quiet, I guess I'll just start with the introduction. Oh, yeah, so I should ask who is, well, familiar with symmetric monodal categories? Okay, I was hoping it would be a little more. Okay, so who is familiar with just plain ordinary categories? Also, not everyone. Yeah, then we'll have to see how it goes. I'm I'm happy to yeah. Also happy to explain things in more detail, kind of then during the breaks, maybe. But for now, I've kind of been assuming that you've seen symmetric monodal categories before in some way. But if I mean, okay, I hope we can also kind of now spontaneously adjust a little bit and go into a bit more of not the full formal definition of symmetric monodal category, but at least like can try to make it to convey the idea and make I'll try to make that understandable. Okay, so the sort of setting. Imagine that you're looking at some kind of cooking recipe. So this is the sort of how some people like to explain this in a context of cooking. Well, maybe you want to make pancakes, and then you start with an egg, right? And then maybe you would draw some kind of flow diagram where you draw the ingredients. So now, like as a physicist, I'm going to draw time in the upwards direction. So we're going to maybe start with an egg and a flour. And then, well, we don't want to use the egg as is because it's in a shell, so we have to crack the egg. And then we're going to mix the resulting cracked egg with the flour. And then, well, all of this goes in the pan, right? So we have the pan as a separate item. But also the pan, well, so the egg kind of goes into the mix, and what comes out is the dough. And then we use the pan and the dough to actually make the pancake. But not only the pancake, because obviously we don't destroy the pan, so the pan comes out again as well. Okay, right. So this would be how you can draw a kind of cooking recipe as a flow chart, something of the sort. And now, as a category theorist, we want to interpret this entire diagram as depicting a function that goes from states of the pan, that goes from kind of a joint state of the pan, of the egg, and the flour to a joint state of the pan and the pancake. Right, so then in this interpretation, each of these words actually stands for an entire set of states. So the pan could be, well, I don't know, could be maybe clean or could be still greasy or something. This would be possible states of the pan. And obviously afterwards it's going to be dirty. And pancake could have states like, I don't know, maybe it's burnt or maybe it's just a good normal pancake. And so then like this is just this overall diagram depicts a function from the joint states to joint states, right? And it's kind of obtained by composing. It's built out of smaller functions. Well, okay. The cooking function is maybe the clearest. That there's various possible outcomes for what a pancake can look like. And so typically this might not be a deterministic function after all. And so if you're used to maybe thinking about quantum channels or this kind of thing, then this would be the quantum version of this, right? Where you have quantum systems that can be in various states, and these boxes depict quantum channels, and then the overall diagram denotes a composite quantum channel that is obtained, well, by composing the diagram into one thing. Yeah, okay, so as classical or quantum computer scientists, I guess we would also call this a circuit diagram, right? Okay, and so now a symmetric monoidal category, and I'm going to abbreviate it as SMC. It's just basically an algebraic structure where this kind of thing makes sense. Right? So algebraic structure. Where these kinds of circuit diagrams can be interpreted. Okay, and so that means we have two types of things in a symmetric monoidal category, right? We need to have these sets of states. So these we call these objects, which doesn't mean anything physical, right? It's just a mathematical term for, could be a set. Or in a quantum probability context, and I'm going to write down the example soon, but quantum probability context could be a C-star algebra. And then we have these boxes. Well, then, in a category theoretical context, so we call these morphisms. And so basically a morphism can take multiple objects as input and produce multiple objects as output as well. And the fact that when we draw two wires in parallel, this means that we can consider them as a single object. And so this is part of the symmetric monoidal category structure as well, that we can consider parallel wires as single wires. This means that basically we can combine objects as well, and this is kind of often a kind of tensor product. But it can be, in principle, it can be any sort of binding operation on objects that you want. Okay, does this make sense so far at a somewhat informal level, maybe at least? Okay, then I'm going to write down some more examples, write down some actual examples of symmetric monodic categories, and then basically then I'm going to argue that that's not quite enough to do probability theory with, although it takes us kind of part of the way. Oops, I just accidentally closed the, okay. All right, so concerning the examples, I already said that the cooking thing kind of may do something random, right? The outcome, what kind of pancake comes out of it, especially maybe when you're the chef and you're not so skilled, that's maybe a little random. So this means that these morphisms are not necessarily actual functions, but there could be some inherent uncertainty or randomness or something that these things model. So these may contain uncertainty or randomness. Okay, so let me give some examples of symmetric monodic categories in the spirit. So maybe the most basic one would be the category of sets. So then, so we usually denote particular categories and by some kind of uppercase letter that tells us, often just tells us what the objects are, and then the morphisms are kind of understood to be some kind of structure preserving maps between these objects. But then, as we'll see, we often also kind of denote the morphisms. But so here we have just sets as objects. As I had indicated earlier, this would be kind of sets of states of these things, for example. And then just functions between these sets as morphisms or maps. So honest actual maps between sets. Well, in this case, there's no uncertainty, right? A function produces a unique output for every input by definition of function. So this is a kind of example, also example in our setting, but a kind of trivial example because there's no probability in there. The next kind of less non-trivial example would be what we denote by finstock. So fin standing for finite and stock for stochastic. So then here we have the probability. So here in this symmetric monodic category, the objects are finite sets. This is the finiteness here is just for simplicity essentially, and you can kind of easily generalize this. Now for the morphisms, we want to allow randomness. So what do you think how we should define these morphisms? If I have two finite sets, x and y, what would be a kind of concept of function involving some randomness between these two sets, x and y?
Stochastic matrix.
Yep, yeah, exactly. Thanks. Right. So, and let me write it down and then say what that is. So, stochastic matrix has morphisms. So I'll write this f x arrow y. So this would take a finite set x values from or elements of x as input and output elements of y as morphisms. And what this is that we just specified a probability of getting an outcome little y for each element or given any element little x of this set of inputs x. So this is basically the collection of all these probabilities, and that's a matrix because it's just indexed by two elements of finite sets. So the indices are just the input little x and the output little y. And I like writing this as f of y given x, because this then already indicates the probability interpretation that this is a conditional probability. There is no unconditional probability here in this case. We're just specifying what are the outcome probabilities, probability of getting little y for an input little x, and there's no absolute probability of y independent of x. Okay. So this is the matrix, well, and of real numbers, but in order for this to kind of form meaningful probabilities, obviously they should be non-negative. So we need to satisfy kind of two simple conditions. Obviously the probability should be non-negative, and they should be normalized. So if I just sum the probabilities over all the outcomes, then for every x, I should be getting 1. Okay, so in a set case,
Tobias, this is what you will also call a classical channel, right?
Yes, exactly. I mean, so actually, it's kind of, to me, it's interesting how many different names there are for this concept. So in information theory, people call this a channel. In statistics, it's basically the same thing as a statistical model. Other people call it information transformer, probabilistic morphism, Markov kernel in a finite case. And so there's so many different names for this. Oh yeah, so if you know what a statistical model is, then it's also the same thing as this. Now, if you because if you now imagine you're fixing x, then you get a probability measure on y on this set y, right? So this x is basically a parameter that parameterizes a family of probability measures on this set y. And that's, yeah.
Sorry, Tobias, what is the monoidal structure here?
What is what?
The monoidal structure.
Yeah, I got you that.
Okay.
Yeah, thanks. So statistical model is the same thing, and this is going to be actually important tomorrow. That we can view this on the one hand as just such a matrix, but on the other hand as a family of probability measures. Okay, now I was actually already in the case of set, I was a little sloppy in that I just told you what these wires are and what the boxes are, but it didn't tell you how to compose them. And in the case of set, it's kind of obvious, right? You just take these functions and put them together in the obvious way, and you get a new function. But in this case, for Finstock, it's maybe less obvious. And so hence also the question here. And so this is something that I still need to define. And there's basically two kinds. So if you look at a big diagram like this is supposed to denote when all of these things are stochastic matrices, this entire diagram is supposed to form a new stochastic matrix. Well, to get that, we basically need to have two ways of composing, two kind of elementary ways. Namely, one is a parallel composition, meaning that whenever we have two things in parallel, maybe we can also add an additional box here. Let's say this is cleaning the pen. Then whenever we do two things in parallel, we're supposed to get a new stochastic matrix. And then when we do two things sequentially, it's also going to have to define a new stochastic matrix. So if you look at the textbook definition of symmetric monodic category, it's actually going to be written in these two elementary ways of composing. There's a parallel composition, and often called tensor product, and a sequential composition, often just called composition. And if you combine these two, then repeatedly, then you can evaluate any diagram. So to define this, what I wanted to say with this is, in order to tell you how to compose things, I only need to tell you how to compose two stochastic matrices sequentially, and how to tensor things. Okay, so let's start with composition. The sequential, so when I say composition, it just means sequential composition. So suppose that I have a stochastic matrix F from X to Y, and now a second one from Y to Z. Then we should get a composite G composed F, right? Going from taking an element of X as input and producing an element of Z as output. So now again, we need to define the probabilities here. Well, to define what this stochastic matrix is, we just need to say what the probabilities are. So what do you think is a reasonable definition for, or what would you expect when you compose two F and G sequentially? And I feed in a little X here. What is the probability that I'm going to get an element of Z?
What are probabilities?
Hmm?
The product of probabilities.
Yep. So we multiply the probabilities, but then since we're kind of not looking at what the intermediate value here is, we also need a sum over that, right? So okay, yeah, let me write it. So it's a G of Z given Y times, this is kind of the canonical thing to do, times F of Y given X, and I'll sum over Y. But of course, if you know view these as matrices, this is just matrix multiplication, right? So yeah, composition is by matrix multiplication, and it's obvious to see that those two properties again hold for the new matrix that we get. All right, just a straightforward calculation. But so in terms of probability, the important thing here that I want to note is that we multiply these probabilities. And multiplying probabilities is independence, right? Stochastic independence. So when we prescribe this formula, when we define composition like this, what this means is that we are assuming the randomness in these two processes to be independent.
They point out that it was actually the main assumption by Feynman about the composition of amplitudes.
Okay, yeah. Well, or maybe Feynman would have derived it from the action in QFT or something, right? Is there an eraser?
Yeah, here.
Thanks.
I think this one's probably going to work better.
This one?
Yeah.
Okay, well, but now you might object, well, but if I don't want these to be independent, I'll get to that soon. Okay, now what about the parallel composition? If I do two things in parallel, so suppose now here we have finite sets A and X, B and Y. Well, then again, I need to be able to interpret this thing as a new stochastic matrix, which now goes from A times B to X times Y, because, well, basically this parallel tensor, or this tensor on wires is just, we take a Cartesian product, which makes no sense if you think in terms of kind of classical states, right? Then we have a joint system. All the possible states of these are just pairs of states of A and B. Okay, so this means that our F tensor G is going to take a pair XY, or give a pair XY as output for every pair A, B as input. And again, the kind of obvious thing to do is to multiply the individual probabilities, right? And this is, I mean, also in the quantum case, which maybe we can talk about in a few minutes, you're just going to tensor the two channels. But this is what we're doing, just tensoring the channels. But at a level of individual probabilities, that again amounts to multiplication. Okay, so yeah, as I said, we have stochastic independence here. When we draw them like this, we would this amounts to assuming independence. That the randomness inherent in F is not correlated with the randomness inherent in G. But what if it is? So what if we want to model? What do you think we could do if we want to model a situation where there is some dependence? So now using symmetric mononomial categories, if I want to claim that this can deal with kind of probability, then I need to be able to also model dependence, right? So yeah, let's look at maybe a concrete example. Let's look at maybe kind of, well, let's take our Alice and Bob, and maybe they're playing a lottery. And we have on the one side, Alice can choose how much he's going to bet. And then she will get a price, which of course might be zero. So, or typically, I guess, will be zero. And then suppose that she has a certain lottery ticket, or no, she makes a certain bunch. I mean, and consider those kind of lotteries where you have to cross out a bunch of numbers. And let's say her guess is she just chooses the numbers. I don't know, 1, 2, 3. Okay, and now this is, I mean, obviously we can model this as a stochastic matrix. Depending on how much it's going to bet, there will be probabilities for what her return is going to be, and we can calculate them if we know exactly how the lottery works. Okay, now let's look at Bob's side. So for Bob, we're going to do the same thing. Bob takes a certain bet as input, and then going to get some kind of price as output, and now guess Bob's guess. Suppose that Bob's guess is always I don't know, 3, 2, 1. Well, okay, maybe it's silly because the set of numbers is the same. So let's say it's 4, 5, 6. Okay, now suppose that we want to model these two things together. And so in this case, you think it's appropriate to use this tensor product. So can we basically assume that they're independent? Why not?
Not really,
No, why not?
because it depends on how the prices are distributed. If there is a given price,
Yeah.
it probably means that there
Right.
is another price, maybe.
Yeah, exactly. So exactly that's the idea. For why I chose this example. If Alice wins the jackpot, well, then Bob will not, because his numbers are the wrong ones. If Alice's numbers are correct, then Bob's numbers are not, and vice versa. Right. So there is some dependence here. Whereas if we just tensor them like this, then of course we'll get non-zero probability for both of them to win the jackpot. Which doesn't make sense. So how do we account for this? That means we need to draw a different diagram, right? And well, basically there must be a common cause or something. Or basically what I'm gonna do now to fix this is I'm gonna draw what quantum information people will call the Bell scenario. So I need to allow some kind of hidden variable between the two. And this hidden variable is basically the actual draw of the lottery, what numbers are actually drawn. Right? If you know these, then this solves the problem, and you can define these guess functions as perfectly sensible stochastic matrices that now have an extra input, namely the actual draw. Okay. And now maybe there's still something random in here and in here. I don't know, maybe there's cases where Alice accidentally processed the wrong numbers or something like that. But then it maybe makes more sense to assume them as independent and thereby to use this kind of diagram to model the situation, right? So whenever we use a composite diagram, that means we're implicitly assuming the randomness inherent in each of these things to be independent. Okay, so yeah, what I want to say at the moment is that so far we're developing, I mean, just a simple graphical language for not just for probability, but we can do this for other symmetric monodic categories as well. I mean, now, yeah, maybe let me turn to quantum probability for now, and briefly talk about this. Then before going to some other examples. So this is still now another item in the list of examples. And so, well, first for quantum probability, we can do something like C-star algebras as objects, or just if you want, just think of take finite dimensional Hilbert spaces if you prefer that, and completely positive unital maps as dimorphisms in the opposite direction. So this is going to be in the Heisenberg picture. So C-star algebras as objects. And yeah, since we're talking about observables, it's kind of most natural, I suppose, to work in the Heisenberg picture. And so that means that the morphisms are quantum channels. No, sorry. To be clear what I mean by quantum channel, I should say CPU, completely positive unital map in the opposite direction as morphisms from A to B. Yeah, is this clear enough? And then obviously we know how to compose these, how to tensor them. Yeah, please ask if not, but otherwise I'm going to assume that this is the thing that people are most familiar with here. Okay, good. Yeah. Yeah, so this is also a symmetric monodal category. And maybe so far it all looks a little silly. Why are we using this kind of just talking about these diagrams? But yeah, we'll get there, and I'll demonstrate how this is actually useful and how we can prove theorems in to some extent in purely by just diagram manipulation. Okay, but let's look at one or two more examples. So another kind of classical example is what we call thin-set multi. So the difference to Finstock, and Finstock we were talking about probability, numerical probability, and thin-set multi, we're just basically looking at possibility instead. We're looking at what outcomes are possible, what outcomes are impossible. So just kind of modeling uncertainty in this coarser way. And the nice thing is that this can be defined in basically exactly the same way as Finstock, that we have matrices. But now instead of having numerical probabilities, we only record, well, as I said, what is possible and what outcomes are impossible. So this means that with f of y given x, an element of just a two-element set, so let's say just 0, 1. So 0 means outcome y is impossible on input x, and outcome y, 1 would mean y is possible. Okay, And maybe just also write this down here. So impossible. And 1 means possible. And now, well, we want to use the same equations as before, right? To define the sequential and the parallel composition. So that means we need to know how to multiply and how to add these possibility or impossibility numbers. Well, multiplication, I guess, is quite clear, right? We can also look at it here. If one of them is impossible, then also the whole thing should be impossible, right? While if both are possible, then the whole thing should be possible. So multiplication is just how we would usually multiply 0 and 1.
You're not asking for any normalization, right, as opposed to before.
Yeah, right. That's a good point. Yes, I'll get to that too. But on the other hand, addition. So for addition, recall we use addition in order to do sum over y here, sum over the intermediate possibilities. And so then here we should say, well, when is this possible to on an input little x and an output little z? Well, if and only if there exists a y for which one of these things is both of these things is possible. And this existential quantifier basically translates into saying that we add these numbers in such a way that 1 plus 1 is 1, but otherwise, well, 0 plus 1 is 1, and basically 0 plus 0 is 0, of course. Right, so when we add a bunch of these numbers, we get 1 if and only if there's at least one 1 in the sum. And this implements our existential quantifier there. Okay, so this is then now it defines what's called a Boolean semi-ring. Right, Boolean just because it has these two elements, which in some sense we can also think of as true and false. And we just use the usual arithmetic except for 1 plus 1 being 1. Okay, so now Arnaud had asked about the normalization. Maybe we also want to have the normalization of probability here in the sense that, and so this is something that indeed we do impose, but if you wanted to, you could also do without at this point. So we also do impose this equation. So now what this means is that for every input little x, at least one output little y should be possible, right? So if maybe a computer scientist would say that the automaton never terminates or something, you can always keep going. It always keeps going in some way. You can always proceed. Some outcome is always possible. Yeah, but in case that you don't want this, then as far as what we've talked about so far is concerned, you can also do without this and say that I allow things to kind of get stuck. Okay, by the way, we're talking about semi-ring here, and maybe it's clear also from the previous discussion on Finstock that we're not really using anything specific about what these elements of what exactly this arithmetic is, as long as it satisfies the usual rules. So in principle, yeah, we can do this. We can do the exact same thing for any semi-ring, which means so we just need an addition, a multiplication, satisfying usual associativity, commutativity, distributivity, and existence of neutral elements, and then we get a symmetric monodic category as well, formalizing some kind of uncertainty. Okay, so one more example. And as I'm just erasing this, there's measure theoretic probability here, right? Obviously, if we want to postulate that we can do probability theory, we can't just stick with Finstock. I mean, that's any probability theorist would laugh about that. You're just dealing with finite sets. So we need to do measure theoretic probability as well, and so this is going to be the last example, which for us and what we're doing is kind of our main working example. Okay, yeah, so that's a another category that we call Borel stock. So here, this has leaving a little space here, intentionally measurable spaces as objects. Right now, in the infinite context, we just can't use sets anymore, of course, and we talk about probability measures, which are defined on measurable spaces. But for still measurable spaces, there's kind of too many of them. There's many pathological ones. And somehow we want to have just nice measurable spaces. And so what we do is that we restrict to standard Borel measurable spaces. I don't really want to define these, but to give an idea of what these are, let me just quote Kuratowski's theorem, which characterizes them. Kuratowski's theorem. Kuratowski's theorem says that up to isomorphism, there's only a few examples of these. These are namely the finite sets. So then we're basically going to be back in Finstock. And then only two more, namely the natural numbers or any countable set, and the real numbers. Or if you want the unit interval, then that's measurable spaces, that the real numbers or the unit interval, or even take Cantor space. So countable power of a finite, non-trivial finite set. These are all isomorphic as measurable spaces if you equip them with just the usual sigma algebra, the Borel sigma algebra. By the way, there's so this is, well, of course, in a purely classical context, but there's kind of a question, and I'd be curious if some of you have an opinion on this, and then please speak up. What is a quantum measurable space? What would be a quantum version of quantum non-commutative generalization of this definition? Even if you want, you can also just answer it without standard Borel. Does anyone have any proposals? Yeah, right. That's I was hoping someone would say that, but I actually want to argue that's not the case, because the what you get for Neumann algebras from a probability space if you quotient by almost sure equality, right? but here we don't have any fixed probability measure. So we cannot quotient by any sort of almost row equality. But for us in this setting, I think the most natural kind of C-star algebra to look at would be the C-star algebra of bounded measurable functions without the quotienting. And while this is certainly not a phenomenon algebra, right? It's not monotone complete. So yeah, there's the concept of sigma C-star algebra where you basically only have countable monotone completeness, and this seems to be a little more like what we would want, but still not quite probably. This is a little open, but if someone has kind of thought more in this direction, I'd be interested to talk. Okay, so yeah, this is what we have at a level of objects or state spaces, if you want. And now what about the morphisms? So previously we have considered stochastic matrices. Now we can't do quite the same anymore. It's just like a probability measure, well, we can't define it by saying what the individual probabilities of individual outcomes are. We need to define it on the measurable sets, right? So likewise, here, this is really what's generally called a Markov kernel. Meaning it's actually a map which, as before, takes an input from X and now returns a probability measure on Y. That's the idea. That means we need to have an additional argument that is a measurable set on Y. And so here my sigma Y denotes the sigma algebra on Y. Right? And so then we get a probability. And just to introduce a little bit of notation, so for elements little x and measurable set S, I'm also going to denote this sort of thing. Now when we're given this F, I'm going to denote this probability as F of S given X. Right, so the probability to get an element of S when the input is little x. So now, as before, I mean, these are for every x are statistical models equivalently, right? In the sense of these are parameterized probability measures depending on the parameter x. Okay, so now, yeah, let me just write this down. This condition that it should be a probability measure. So if you fix the second the x argument, but leave the other one open, then it's just a map on the sigma algebra to the unit interval. So this should be a probability measure. For every x. And well, it's natural that there should also be an additional condition on how this depends on x, and well, it should depend on x only in a measurable way, meaning that for every measurable set x, s, sorry, and if I vary the other argument, then this should be a measurable function. Okay, so composition. So for thin stock, we had done this with matrix multiplication, and here it's kind of similar. Again, kind of multiply the probabilities and then sum, but well, now the sum becomes an integral, but it's. Let me just write it down. So, gonna be looking like this. As so g of t given y. And so now instead of summing over y, we integrate over y. And I like denoting this by a d. So I like writing the d to the variable rather than to the measure to indicate that we're basically plugging in a very small measurable set dy into this argument of f. Okay, yeah, so this is the Chapman-Kolmogorov equation, which maybe indicates that it goes back in history about as much as the concept of probability measure does. And this is how we compose, and again, here, because of the multiplication, we have the assumption of independence in here. Okay, the tensor is basically similar as well. And so let me just write it down. So this is, previously we had multiplied the probabilities, now we're doing the same thing. Oh, I should say both of these are definitions, right? So I'm putting just a colon equals there. Times F times G. Sorry, I'm getting this.
A and B, right?
Thanks, yeah. Okay. All right, well, now you might say that, but I haven't defined F tensor G in general because I'm not plugging in an arbitrary measurable set here. And that's that would be a good objection. But this is just basically standard theory of product measures, which says that there exists a unique measure satisfying this equation. So basically, I'm just taking the product measure for any given values of A and B. Okay, and yeah, so this defines a symmetric monoholic category. And so now we can deal with measure theoretic probability. All right, so this would conclude my list of examples. Are there still any questions so far? Yeah.
More curiosity, why do you need the standard measurable fields? I mean, would you need them here instead?
No. So far, this works for immeasurable spaces. What gets more difficult in particular would be the existence of conditionals. I'm going to define this, I guess, tomorrow. What conditionals are, so this would fail if you allow all measurable spaces. There are still intermediate classes where it still works, but then some additional axioms that we work with just would not hold with all measurable spaces, like the existence of conditionals in particular.
Just so you may comment in the name, symmetric monoidal category, monoidal, the product, the symmetric part, where it comes from.
Right, yeah, thanks. Yes, I've been a little maybe sloppy on this by not distinguishing monoidal and symmetric monoidal categories. But the difference is that in a monoidal category, we can only evaluate, well, diagrams like this, where these wires do not cross. But what we have in a symmetric monoidal category is that I can also make sense of such circuit diagrams where the wires do cross, and I can manipulate the crossings in the usual, in kind of the obvious way, that instead of crossing down here, I could pull it up there and cross, or I could pull the cleaning box to down here and would get the same overall morphism, the same composite. And this is what the symmetry stands for. It's kind of symmetry that I can permute. At every kind of time slice, I can permute these wires as much as I want. Okay, so, but now why is my title Markov categories and not symmetric monodic categories? The reason is that the symmetric monodal structure is actually not expressive enough. And I'll illustrate why. Not expressive enough for the purposes of classical or quantum probability, I would claim. And to say what I mean by this, let's look at one of the kind of first examples, first concepts that you might come across when you study probability theory, or well, maybe not so much in probability textbooks, but in other kinds of sources, you would soon read about conditional independence, for example, right? So, e.g., now let's write down what conditional independence would mean in the context of Finstock. And then we can try to see how we would express this in the symmetric monodal category language. Independence. So suppose that we're looking at a stochastic matrix that would have one input and two outputs. So input from a finite set A and outputs in finite sets X and Y. Now we can talk about the conditional, that we can talk about X and Y being independent, conditioned on A, or conditionally independent given A. The idea being that in whatever way X and Y depend, have some dependence, this dependence can be traced back to A, or it kind of originates with A. Similar to how in the lottery example, the dependence between Alice's and Bob's prices originates in the common draw. Right? And so mathematically, what this means for the probabilities is that these should factor probability to get X and Y should be the probability to get X, right, times the probability to get Y for a given A. Is this clear that this amounts to conditional independence? Okay, yeah, so now the question is, how would we express this? I mean, is there some kind of diagram, equation between diagrams that we can draw and that would recover this equation in Finstock and specialize the analogous equations in our other categories? And the answer is no. And but there is a way that maybe we would want to express this. So of course, on the left-hand side, we just have our original f, right? So the left-hand side is pretty trivial. But the question is, how do we draw the right-hand side? So if we look at what's going on here, an important point is that this a, the value of a, gets used twice. And this is why, or one reason for why we cannot express this equation in terms of the symmetric monodic category language. Because the value of a would kind of live on a single wire.
Sorry, could you draw the types on?
Oh, yeah. Right, well, the little a would live on a single wire, but there's no way to kind of, we want two wires here to take an A input. And also the F, if you look at the outputs of F here, this F only has an X output, but our F has two outputs, so what do we do with the other one? So there's two problems that we have here. In a sense, we would kind of just like to get rid of the other one. And so these two problems are both solved by the definition of Markov category I'm going to get to. But the way that we would want to draw this.
Sorry, why?
Yeah.
So why are you writing f? Is this the marginal of f x y?
It's right, yes.
So a priori, you're not assuming that. So couldn't you have just written that as g and h, g of xa and h of xa?
Yes. I could have written it as a condition saying that there exists g and h such that, but then we still have the problem about the
Yeah.
That's a good point. Yeah, thanks. Okay, so the problem about the A is that we need a way to talk about kind of copying the value of a variable, or kind of turning one wire into two. And suppose that we have this, and suppose that we draw this as a kind of dot, and just as a kind of splitting of wires. Then we can actually make more sense of this, or at least in the version that Arnaud has proposed, we could draw this. And in this version, we still can't quite do it because we still need to get also rid of these double output, get rid of one of them on each side. And so in addition to this copying, we also postulate that there's a discarding kind of structure, which means that you can have a wire and you can just let it terminate. And so I'm also just going to draw a dot here, and the wire just ends here. And likewise, so likewise here for the X wire. So the ones that come out are the X and the Y here. And now this is the sort of language that we actually want to have. When I have these additional structures, and this is going to be the definition of Markov category, or the language of Markov categories is precisely what gives us this. And then this is exactly the representation of that equation.
Sorry, do we also require the duals? Do we also require like the multiplication and the?
No.
Okay.
So
it's only a coalgebra, so to speak.
This is something that's been quite interesting to me in a sense. In principle, maybe you would also think or consider maybe you would want to have something like this, and maybe you would want to interpret this as a kind of equality test. Right? If you got two values that are the same, then you pass the same value on, and if they're different, then you do nothing and kind of terminate. One can do this. And there's people who have considered this also in this context now, but it turns out to be surprisingly irrelevant for probability theory. And actually, in a quantum probability context, I would no longer know how to actually do this. So yeah, this is these ones are what we want, a kind of copy and a deletion marginalization operation. And so this leads to our definition. Sorry, no, I shouldn't say our definition, but well, yeah, I'm just going to skip the history and all this here and just focus on the math. But here I shouldn't say our definition, but a CD, first of all, a CD category. So where C and D stand for copy and discard. Right, basically these two pieces of structure. CD category curly C is a symmetric monodal category, an SMC. Together with, well, then so-called copy and delete morphisms. So every object X should have such a designated copy morphism that we just draw as this kind of dot. And a deletion or discarding morphism and of course you should satisfy a bunch of compatibility conditions such that well, yeah, and so these compatibility conditions just kind of formalize intuition about how copying and discarding of the values of variables behaves. Right. So one thing is that if you copy a copy of something, then of course you could have just as well have copied the other copy. So this is associativity. If you take a copy and delete, if you copy and delete one copy, well, then that amounts to doing nothing. Likewise for the other one. And now if you take the symmetric monodal structure in order to swap two copies, then that's again just copying. Right, so the two copies are permutation invariant. This is something that's no longer going to hold in the quantum case, maybe unsurprisingly. Okay, and well, so these equations are just saying that for each object we get a commutative comonad, right? Kind of associativity, unitality. In the reverse direction, that means we have a comonad, and here we have the commutativity. Okay. And well, so now we have this for every object, but of course there should be also a compatibility condition across objects. And so this is one additional thing. That if you look at a copy of a tensor product object, this should basically factor into. All right, so imagine you copy values of x and y at the same time. Well, that just amounts to copying a value of x and copying the value of y. And what this, so the right-hand side diagrammatically, then what this looks like, just like this, copying a value of x and copying a value of y separately. And we kind of need to swap them here so that I still have the right order x, y, x, y. Okay, and likewise for the discarding, if you discard the values of x and y, well, then that clearly should correspond. Sorry, no, I should draw this at the bottom. X tensor y as input and no output. Then of course this amounts to discarding these separately. Okay, this is the kind of these are basically multiplicativity conditions. Now, whenever you have a condition saying that something like is multiplicative, typically you also have a condition that preserves the unit. And so we also have this. We have a monoidal unit, which is kind of a trivial object designating an empty wire. If you haven't encountered symmetric monoidal categories before, then maybe just ignore what I'm going to say now and write down. But so this is our monoidal unit object I. And the copy on this should just be its identity morphism. And also its discarding should just be its identity morphism. Okay, so this is the definition of this copy discard or CD category. And now I can finally get to one more thing that makes it into a Markov category. And we call it Markov category precisely because it means Markov kernels. Right, so it's an abstract concept of category that's abstracts away from category where morphisms are Markov kernels. And so the final condition is to C as a Markov category. By definition, if in addition we have that when you take any morphism and you discard its output, well, that's the same thing as if you had just discarded its input to start with. And this is kind of intuitive, I suppose. You take some physical process, you discard its output, then well, that's as if the thing had not happened at all.
Are you assuming, so these are, I assume, natural transformations?
No,
You're
no.
not assuming, okay,
I'm only assuming these conditions
okay.
and no naturality.
Doesn't this amount to saying that?
This
that
is the naturality of the deletion, but the copy is importantly not natural.
Okay.
And I'll get to that. Yeah, so and if you look at what this means for Finstock or for Borel-Stock, this holds basically because of the normalization of probability. Right? If we had just forgotten or not included the normalization of probability, then we could have such Fs where this would not hold. Because, for example, we could have F that produces an output only with probability less than 1, or maybe with probability 0. And in that case, that would not be the same as discarding input, because in that case, this F would get stuck. But yeah, since we consider normalization of probability, that's why we have this equation. And in actual reasoning about probability theory, we use this a lot. Okay, so maybe the final thing for today, let's say that all the categories that I had introduced so far are Markov categories in an obvious way, in the sense that there are obvious copy morphisms. Right, for a stochastic matrix, So in Finstock, for example, well, it's just a stochastic matrix, which takes an input x and has probability 1 precisely on the pair x comma x and probability 0 and everything else. And it's similarly in Borel-Stock. And what do you think it is in the C-star algebra example? What is the copy going to be?
Tensor products, but that's not quite right.
No, so what it must be is if we have the C-star algebra A, it must be some sort of distinguished CPU map, right? From now in the Heisenberg picture, we're going the other way. So from A tensor A to A. What could it possibly be?
Multiplication.
Yeah. Yes, exactly. So it's going to be, I mean, this is, and here we see why Markov categories are classical probability. It's, first of all, multiplication is commutative only in the classical case. And it's, of course, also completely positive only in the classical case, only if the algebra A is commutative. But in that case, our multiplication is, our copy is exactly the multiplication when you view it in the Heisenberg picture.
This is why you drew the arrow backwards for the C-star algebras.
Yes, right. Well, I would say more like the other way around, in the sense that the fact that we draw the arrows backwards results in this being the multiplication, or yeah. Okay, so yeah, then maybe this is a good point to stop for today. So I've introduced the definition, and then tomorrow can continue with kind of additional axioms on Markov categories that may or may not hold. Okay.
Thank you
Thanks.
very much.